we were doing experiments from roughly the early 90s after we'd gone along with Dr. Morenchich and conceded that, yes, what Tesla was doing was surface waves. We started doing experiments from the early 90s to here we are, November 1st, 2003. And I got a call, that was a Saturday morning, I think, that I got a call from Ken. He had been doing these experiments. We were measuring the field strengths with the Potomac Instruments FIM 41, NIST certified. And we're doing these experiments. And we got these results, and it was our first result where we actually saw a Zenek wave. You can see the data. By the way, we didn't know how to predict it at that point in time. But Kenny's just randomly measuring the data out to about 20 miles here. And the field strength is, you can see, is about 40 dB stronger than what you'd get from an incremental stub antenna, which is what we were using, or what we were using could be classified as one. We got this result, and we said, aha, it's really real. It's there. And the question now is, okay, let's take it to the next level. Well, this was in November 2003, and that was a year where there was a lot of rain, and winter came in with a blast, and the ground froze, and we couldn't perform the experiments until late the following March or April, when the snows, where Ken lives up in the mountains in New Hampshire. And, we couldn't get the results again. Now, we had a lot of confidence in the data and in the experiment, but we didn't know what we were doing. And it took about another 8 years before we could finally replicate this, and the lights came on, and we finally began to understand what was happening. This leads us to the problem of the Sommerfeld sign error, which Sommerfeld never admitted. He never accepted that he'd made a sign error. We call it the pathology of the Sommerfeld sign error. Pathology is from the Greek word pathogelia, meaning study of suffering or diseases and so forth. The argument of Sommerfeld sign error was a potent argument. So here's in a nutshell, electromagnetics during the 20th century. 1889 is when Hertz's solution for the doublet in free space is published. 1901 is Max Abraham's solution for a monopole over a perfect ground conductor. 1907 is Zenek's presents the surface wave solution, but no source is specified. And then 1909 is Sommerfeld's solution for vertical electric dipole over soil. And the thing about Sommerfeld's solution is it exhibits a Zenek surface wave. And that's why Sommerfeld thought it was really good. Now, there's something that is left out, or maybe only tangentially mentioned in a lot of E&M courses, and that is von Herschelmann's solution. Von Herschelmann was a grad student under Sommerfeld. Sommerfeld did the incremental vertical monopole over a lossy Earth. In the meanwhile, there was a development done by Marconi called Marconi's bent antenna, and it was a horizontal doublet or horizontal incremental antenna. Von Herschelmann solves this problem for horizontal. He does the Sommerfeld problem for horizontal antenna as opposed to vertical. It's published in 1911 in 2 parts. We translated it. It's on our webpage. And it is mentioned occasionally. And now he was Sommerfeld's student. Sommerfeld virtually takes credit for it. if you have the 1949 edition of Sommerfeld's Partial Differential Equations, the Volume 6 textbook, you find Herschelman mentioned in a footnote. But Sommerfeld, the footnote is in error. It gives the wrong citation for it. But what von Herschelman studies is a horizontal antenna, and he has to introduce an extra term in the Hertz potential in order to satisfy the boundary conditions. But look, and I'll mention this again a little bit later. What emerges is a surface wave produced by a horizontal antenna, and we'll see how that pops out in a minute. Then 1919 is Hermann Weyl's reformulated Sommerfeld, but asymptotically there's no Zenek wave present. In 1926, Sommerfeld redevelops his solution that agrees with Weyl's solution in the far zone, but there's no dominant Zenek term in it. Now, people were looking for Zenek waves during the teens and 20s, and they didn't see them. And that's when, in 1935, Kenneth Norton at the FCC asserts that there's a sign error in Sommerfeld's 1909 solution. And that's more or less the way it's been taught for the remainder of the 20th century. In 1936, now this is critical, this is called the crucial experiment. It's called crucial not only by the folks back then, but also Jim Waite in his publications. Charles Burroughs performs the crucial measurement to, they're trying to determine whether Zenek waves are real or not. And there's no Zenek wave observed. So Burroughs asserts, and Burroughs was at Bell Labs, and he asserts that Norton was right. There is a sign error in Sommerfeld's solution, but that's wrong. And it isn't corrected until 2004 when Robert Collin at Case Western Reserve in Cleveland, Ohio, does a deep dive into the Sommerfeld solution, and he shows that Norton's sign error hypothesis was, his word, a myth. Aha. So how did we get electromagnetics for 70 years at the upper levels asserting something that was a myth? Here are the people involved. Across the top, Andre Blondel, who was the guy that had been an assistant to Tesla and was the one that hypothesized that a vertical monopole was actually used the mirror image of the incremental dipole. There's Zenek, and of course Tesla, who in 1899 had seen these waves experimentally. Arnold Sommerfeld, and then Hermann Weyl that has his solution in 1919. Bruno Rolf was an engineer that tried to plot Sommerfeld's solution to come up with a set of graphs that would be useful for radio engineers. Now, next guy over there, notice he's circled in red, is Kenneth Norton. And the next one circled in red is Charles Burroughs. I was never able to find Burroughs' closing, his death. He was a fellow of the IEEE, got his PhD at Columbia University, and was at Bell Labs during the 30s. He was in charge of all the radio wave research performed by the Department of Defense during World War II, later became chairman of the electrical engineering department at Cornell University. He was the guy that's responsible for making the Arecibo radio telescope occur in the late 50s. The next guy over there is Stephen Rice, who also did a solution that I think satisfied Norton and Burroughs that there's a sign error. However, these guys sat down. They had a conference at Bell Labs I think it was in 35 or 36. And they sat down and they went through Sommerfeld's solution and could find no mistake. And they went through Hermann Weyl's solution and could find no mistake. And so they couldn't decide on whether Zenek waves were real or not. There was an article written by another guy, Wise, at Bell Labs, that decided that Zenek waves weren't real. Thornton Fry, the guy, many of you will recognize his name from the probability book, the famous probability book used by communications engineers, was the head of the division, I think, and he said, look, when we don't know what to do here, do an experiment. So Charles Burroughs did. And in 1936, he went to Bud Lake in New Jersey and tried to experimentally verify. And Bud Lake was too shallow, and they were getting a lot of extraneous data. So they went to Seneca Lake, one of the Finger Lakes in upstate New York. And we'll talk about that in just a second. I want to mention these other names. Fritz Noether, he was the brother of Emily Noether, who with all the Noether theorems and so forth. Leonid Mandelstam in Russia he was the head of the Nonlinear Oscillations Institute in Moscow. He died in, I think, 1944 or so. And he was looking for Zenek waves and couldn't find them over land. The next one is Georg Gubau. And Gubau came to the U.S. under Operation Paperclip along with Werner von Braun and a bunch of other people whose names I can't remember either. And then, of course, Jim Waite. And these guys are all referencing the sign error that was due to Kenneth Norton and Burroughs all the way up until we get to Robert Cohen. Okay, well, here was the experiment they did. Curve number 4 is the free space curve. Curve number 3 is the Zenek curve. The dots are the data that Burroughs measured, and the curve that connects them is the curve predicted by Kenneth Norton using the sign error. Burroughs publishes a paper in Nature in 1936. It's also published in greater detail in the proceedings of the IRA. And he makes the comment that the prediction of a surface wave was due to a mathematical error. That's not right. These tests prove conclusively that simple antennas do not generate a surface wave, and that this time-honored concept must be given up, at least in the sense that radio engineers have customarily used it. And that's wrong. Okay, so we have an apparent paradox. Here we are sitting, let's say, in 2003, 2004, when we're doing these experiments, we have a paradox. We have an analytically defective theory, that is Norton's, that predicts what is observed, and we've got an analytically correct theory, that's Sommerfeld's, that predicts what's not observed. The question is, well, what happened? What's going on? So now we're down to this mystery of the crucial Seneca-like justification of the sign error myth. The power of science is that it doesn't depend on what people say. The motto of the Royal Society dating back to 1660 has been nullius in verba. Take nobody's word for it. Go do the measurement. Okay. Feynman, in his lectures at Cornell University in 1964, made the following comment, and this is most physicists would recognize this. He says, if it disagrees with experiment, it's wrong. It doesn't make any difference how beautiful your theory is. If it disagrees with experiment, it's wrong. That's all there is to it. That's it. But then Feynman goes on and makes another comment. He says, wait, there may have been some feature. And later on, he said, as I get older, I realized that being wrong isn't a bad thing like they teach you in school. So there's hope for the D and C students. Okay. It's an opportunity to learn something. Okay. Remember in day one, the first thing they gave you in the first grade was a pencil. And on the end of the pencil was an aid that could help you correct mistakes. Feynman, the next paragraph, and this is the part that most people quoting the first paragraph from Feynman tend to leave out. He says, however, one has to check a little bit to make sure that it is wrong, because someone who did the experiment may have reported it incorrectly, or there may have been some feature in the experiment that wasn't noticed. All right, so in 1936, Charles Burroughs and crew went to Seneca Lake, one of the Finger Lakes in upstate New York. Now the thing about this lake is the mu and epsilon and the sigma, the constitutive parameters, are very uniform. The lake is about, in some places, 600 feet deep. It's so it's very stable. It's not like the problem he ran into in New Jersey at Bud Lake, where it was, I'm going to say 8 or 10 feet deep or something like that, and you could see the bottom with radio waves. This is deep enough so that we've got this is the closest we could come to, at radio frequencies, controlled conditions. Notice where Salt Point is. I mention that because Salt Point is this little thing you see off on the left-hand side there. There are salt mines down underneath the lake, and it's where a lot of the salt comes from for putting on highways at winter times. So Ken packed up the equipment. We'd been doing the Burroughs experiment over ground. We were getting consistent results, and now we believed the results we were getting, and we believed that that's what Tesla was seeing. So he packed up the equipment and he went to Seneca Lake, to the very spot where Bell Labs had conducted the experiment in 1936. As Burroughs in the little boat behind, they're dragging around field strength meter, making measurements. Now, they conducted this experiment at 150 megahertz, a wavelength of 2 meters. Our equipment was worked at 50 megahertz, so we conducted our experiment at 6 meters. These are the results from Burroughs' Seneca Lake experiment, summer of 1936 at 150 megahertz. Again, the curve number 2 here is Sommerfeld's prediction. The dots are the measured data going out to 2 kilometers, which is, from one side of the Seneca Lake to the other. And the curve is Norton's curve using the mythical sign error correction. Okay, so here's Kenny. This is actually Kenny in the speedboat out there taking data. We used a Potomac Instruments FIM 71 VHF field strength meter, calibrated. This calibrated. This is on September 4th of 2014, and we're repeating the Burroughs experiment. The only difference is this. Instead of using a conventional half-wave dipole, we're going to use something out of Tesla's Colorado Springs notes. And if you've got the notes, you can look on the entry for September 29th, 1899. It's the end of September when Tesla's doing this at Colorado Springs. And he has this set of drawings in there. This is not an electrically small antenna. You look at this and you say, oh, he's got 2 balls and he's got a resonating coil. It's not a resonating coil. What we found experimentally is that this is a phase shifting coil. And it's very critical that you can adjust the phase of the voltages on the 2 voltages on the end. And notice that the link couple here is not symmetrically disposed. And most of all, and this is the critical thing that most people don't realize, and Tesla's very careful, he's got this in every little drawing. He's got the E, which is the earth down underneath. So if we were going to use geometrical optics, we would have the 2 balls at different phases and their images at a complex depth. Now, I'm not going to take the time today to explain complex depth, but the notion goes back to A.D. Watt, who wrote that big fat book on VLF radio engineering. And the end result is we can produce an E field out here at this point that has an E sub rho and an E sub z whose ratio is equal to the tangent of the complex Brewster angle, which is equal to the index of refraction. That is critical. Okay, so again, here's Tesla's source, a doublet source, and don't forget the ground down underneath. Well, here's the actual structure. For the two balls, we use two golden doorknobs, okay, and they're only 6 inches apart or so. We're at 50 megahertz. Here's the phasing coil, and we've got a feed line here. We've got to be real careful, make sure that we're not getting radiation from the feed line. And that's Seneca Lake in the background. For the 6-meter antenna, this is a standard half-wave dipole with a choke balun on it and ferrite beads and all this stuff to make sure we're not getting radiation from the feed line. And here encircled in gold here is is Tesla's little doublet. Now, look, the conventional antenna gave us, just as you'd expect, gave us a string of data points as you went out across the lake. Those data points match the Norton predicted curve at about 98% efficiency. We're at 52 megahertz. We're running with about the little doorknobs had capacitances around 3 picofarads, and our source was putting about 10 volts. Now, when Ken went out with a speedboat and took the data, the circles are the measured data using Tesla's source for reference now. The vertical axis is the electric field intensity in dB above a microvolt per meter, and the horizontal axis is the distance out measured with GPS, the distance in kilometers, and we've got a log scale on the horizontal axis here. The circles are the measured data, and let's see, the black curve is the Zenit curve is predicted at 100% efficiency, and the little red curve in here is Zenit at 90% efficiency. We couldn't tell the difference. Okay, now the other thing to notice is, well, look at the knee of the curve here. The difference, I think this is that 10 dB or 5 dB per division? It's somewhere between, it's around 50 dB, 50 or 60 dB difference. So there's no confusion here that, we're seeing something spurious. Okay, so here we are side by side. And what we assert is that, hey, wait a minute, if you do it the way Tesla said he did it, if you do what Tesla said he did, you'll see what Tesla said he saw. And the other thing is that, why doesn't everybody see Zenit waves? And the answer is because they haven't got the correct phase relationship between E sub rho and E sub z. They're not exciting the Zenit pole. And if you don't excite the Zenit pole, you're going to get the Norton curve. All right, well, here we are. This time, let's see, we're in Texas, and we're doing it over land out here out in the field behind the house. And this time we're at 3.75 megahertz, or a wavelength of about 80 meters. And you can see we're getting a Zenit curve with data measured out to about 15 miles in this case. We're only running, I think, a watt. It's not very much. Here's the predicted Norton curve. We had the opportunity to do this down at 100 kilohertz, which is close to the frequency where Tesla was. And we got a curious result from, I forget how much power we were running, but it wasn't a whole lot. This is 1 mile, 10 miles, 100 miles, 1,000 miles. Okay. From 10 miles out to 100 miles, we're matching a Zenit curve. And then a strange thing happened. From 100 miles out to 320, I think it's 325 miles, we match a Zenit curve again, but it's a different Zenit curve. And the question is, what happened? And the guy taking the data was alert and on his toes and said, hey, you know what happened is in this part of Texas, we passed from from gas wells to oil wells. And the underground conductivity has changed dramatically. And we're seeing this. So it looks a lot like the Millington effect for those of you that are familiar with wave propagation. Bottom line on it is we've seen Zenek waves out to 325 miles. And again, if you do what Tesla said he did, you will see what Tesla said he saw. That's from a paper we gave back in 1987. All right, Tesla's puzzling assertions. We've gone through, I skipped a whole bunch of them here, but now we're down to this Prospect Lake demonstration. Tesla thought this was pretty important, and it shows up early on. He talks about this to his lawyer in 1916, but this is figure 4 from his June 1900 Century Magazine article on what he was doing at Colorado Springs. And this is what we would like to explain, and I think we can do it with the physics that we've just gone through, putting numbers into it. This picture in the background here is we're up on top of Pikes Peak, and we're looking down onto where Tesla performed the experiment. Off in here is the Colorado Springs Airport. If you look at it real closely, those of you that have flown into Colorado Springs will recognize it. Tesla's laboratory was over here on the left, and this lake is the lake that appears in the background here. It's Prospect Lake in Colorado Springs. Let's go down to that lake and look back at where we just took this picture from. Okay, so now we're down at Prospect Lake, and we're looking back up at Pikes Peak. Now, Tesla mentioned and this occurs in sworn testimony in patent interference case he has with Reginald Aubrey Fessenden in 1902. And Tesla said, in some experiment, he's explaining some of the things he did at Colorado Springs. He said, in some experiments, I would take my receiving apparatus to a small lake which was nearby. When we were there in Belgrade in 1983 and talking with Dr. Marencic, he said, Jim, do you know anything about this lake? He said, and he called my attention to this quote. And at the time, it was before I had ever been to Colorado Springs. I didn't know anything, didn't know this existed. Well, here's an aerial view of the area. Here's Prospect Lake, pretty good sized lake. Up here at East Kiowa Street and North Foot Avenue is where people believe Tesla's lab was today. Now, of course, none of these houses were here then, and back in those days, there weren't even any trees. If you look closely over here on the side is the printer's home, which you'll see in many of the pictures that are in Colorado, in the Colorado Springs notes. We're not given the exact location of Tesla's experiment here, his demonstration, but we do know it's 2,565 feet from the transmitter source to one end of the lake, 4,375 feet to the other end, and to the middle of the lake about 3,000 feet, which I think is, 3,000 feet. I think that's 914 meters, almost just under a kilometer. Lee Anderson, in his books, uses this number for the distance to where the experiment was done. We'll use that in our calculations. We could use this one and it would be stronger. We could use this one and we'd have to change the parameters, run a little bit more power, or change sigma or epsilon a little bit, because we don't really know what they are, but we can make reasonable assumptions. I mentioned this picture at this point for a number of reasons. All of these guys were intimately related with Tesla. Ernest Lawrence sent Tesla regards. Compton, of course, sent Tesla a note. This picture is taken in 1940, and it's not too far before the Manhattan Project is formed. If you look in the background, you can see the D's from Lawrence's. Lawrence had already gotten a Nobel Prize at this point. And of course, Vannevar Bush, and here's the president of Harvard. Bush was he was a dean, or was he vice president at this point for MIT. And here's James Conant, the president of Harvard. Here's the president of MIT. And over here is a very important character. He's a billionaire. And I wish we had time to talk about him. His granddaughter wrote a remarkable book about him called Tuxedo Park. And his name was Alfred Loomis. He made $1 billion or whatever during the stock market crash, but devoted just a fortune to science. And people like Einstein or Niels Bohr or whatever, when they come to the U.S., they made a beeline to Loomis's home at Tuxedo Park for a number of reasons. I wish we had time to talk about particle accelerators. I'm going to mention a couple of things here in passing. This is the original idea for a linear accelerator from Ising. And Ising is using Marconi's version of Hertz's or Kelvin's oscillator. If you look at this, here's where he's generating an RF voltage to drive a drift tube here. But he's using the Hertz oscillator. And this guy, Viterot, uses a Tesla oscillator. And you can see it right here. He's got the regular oscillator. These are a primary coil and a helical resonator to get high voltage for acceleration. And that is what's used by David Sloan. And if you look at Sloan's operation, this is what, in the mid-30s, 1935, he publishes this in Physical Review. These guys are using Tesla's stuff. Now, if you look at this real close, you can see, well, here's the helix. This is, in fact, the extra coil. And here's the primary that's in the Colorado Springs notes. You'll see is the bundle of 37 number 9 wires that are used laying on the floor underneath at the bottom of the fence. And Sloan originally uses this to get high voltage at this point to generate X-rays. And then he gets the idea to put an accelerating cylinder here. And it's one step from that to a linear accelerator. And then Ernest Lawrence gets the idea, well, hey, wait a minute, I can take these guys, notice their length changes, and essentially make this as a coiled up hose and use a magnetic field to make to direct the particles around and get this accelerator to be wound up in a smaller version. I wish we had time to talk about the change that is made by Louis Alvarez at Berkeley, where he uses a standing wave, and then this marvelous guy, William Webster Hanson at Stanford, who gets the idea, instead of using helices here, and that's really what's going on, we're making the wave propagation. The wave energy goes slow enough so the electron beam can get accelerated by it as it goes along. And this is the linear accelerator that's used over at Stanford across the bay. I mention all this because Chadwick, who discovered the neutron, needed high voltage DC. And he says, I tried to use a Tesla coil, but I didn't have the proper conditions or training to carry out such things. And he gives up and he goes to another technique to get high voltage DC. And the interesting thing about this is, this is the Marx generator version, 1924. It's interesting how all these things get different names, but this is what Tesla patented. It's actually in this 953 patent from June 9, 1987. It's claim number 1, where Tesla says, I charge capacitors and multiple, that is, charge them up in parallel and discharge them in series to get a high voltage. Dr. Alexanderson, who was at General Electric, says, in almost every step of progress in electrical power engineering as well as radio engineering, we can trace the spark of thought back to Tesla. These guys, Cockcroft and Walton, they're famous because they got the Nobel Prize for transmutation of atomic nuclei. But if you look at it again, they're charging up these capacitors in series, in parallel, and discharging them in series to get high voltages DC. What we've got in between here everywhere is a capacitor bank, and they're using vacuum diodes for doing the switching instead of the contactors that Tesla illustrates in his 1897 patent. But it's still Tesla's technique for getting high voltage DC. Niels Bohr put it this way: Tesla's ingenious invention of the polyphase system and high-frequency oscillations had a profound influence on the whole of civilization. And that's a pretty broad statement. By the way, Tesla's genius didn't go unnoticed. Felix Ehrenhaft, who had been one of the nominators for Einstein in 1921 for the Nobel Prize, in 1937 nominated Tesla for an undivided Nobel Prize. It went unheeded. I need to mention this guy at Harvard from Jeanette Conant's book. Conant said, to advance scientific knowledge, pick a man of genius, give him money, and let him alone. All right. That's what this guy did. Who funded Tesla's stuff at Colorado Springs? Well, it was John Jacob Astor. By the way, notice the dates on Astor. He died in 1912. In fact, it was April of 1912. He was one of the people that went down on the Titanic in the icy North Atlantic. But in 1899, John Jacob Astor gave Tesla $100,000 to develop a new system of lighting. Tesla used the funds to create a high-voltage RF lab in Colorado Springs to do what? To light the world. That's where all this was going. So here's the $100,000 lab. This is Colorado Springs in summer of 1899. This is early on because at this point the tower structure is still pretty low. And if you look inside the door, you see he's using a pyramidal coil, which he tears down in September of 1899 and goes to the fence one that's shown in all the pictures that everybody sees. Wish we had time to talk about all the stuff that's inside. These are pictures that everybody's seen. Bergh, who got the Nobel Prize in 1915, Bergh wrote to Tesla in 1931 on his birthday celebration, "Your experiments were the most original and daring," and indeed they were. This is Tesla's workshop. This was published in 1904, but the picture was obviously taken during the summer of 1899. We have the schematic diagram for Tesla's transmitter. And not only that, but we have the values that Tesla measured for all the components. These are in the Colorado Springs notes from pages 352 to 356. So we know we can model this pretty good. So here's the apparatus. All right. Tesla sets it up as he's doing an initial experiment, and he's got, here's the coil, and there's the 10-watt light bulb being lit up 100 feet outside the laboratory. This is not the Prospect Lake experiment. This is 100 feet away. We did the same thing. By the way, this experiment that we just showed you was actually in Tesla's 1893 lecture at Columbia University, which I think is the third lecture at Columbia. And Tesla's talking about his one-wire system. This has come to be called Sipes experiment. Sipe didn't do it till 1903. Tesla did it as a demonstration in 1893, and who knows how much before that. But it was demonstrated at Columbia. It's the one-wire experiment. Isn't it interesting how Tesla's apparatus and experiments and so forth end up 10 years later with somebody else's name attached to them? So this is commonly called Sipes experiment. In the previous picture, you saw it being him lighting up a little light bulb at 100 feet. We did this at 3.5 megahertz up in New Hampshire, and that little light bulb there, that's, I think, a 40 or 60 watt bulb being lit up at 500 feet in August of 2013. This apparently has been rediscovered by a group in North Korea, only instead of using a single wire, they're using tinfoil, but it's the same experiment, I think. Here's Tesla's famous system of 4 tuned circuits, which he patents in September of 1896. 5 years before Marconi applies for a patent that's called Marconi's Fortune circuit. It's the same thing. He was laughed out of the patent office in the U.S. when he tried to apply for it here. It should have never issued even in England because this patent was already in existence in England. What we noticed about this is that there really aren't 4-tune circuits, there's 6-tune circuits. The 4-tune circuits were the Tesla ascribed, so the tuned primary, tuned secondary, and then a tuned, in this case, primary that's in reverse, and a tuned secondary that Tesla's using for the receiver. And he called that his 4-tune circuits. But there's actually 6-tune circuits when you look at it, because you can also adjust the mutual coupling between the primary and the secondary, and you can adjust the spark duration that optimizes this. And we've explained all that in other lectures. We're going to go between the Colorado Springs transmitter and a kilometer away to that figure 4 where you saw the lit up light bulb. But here's a critical thing that all microwave engineers would recognize. This is from an old microwave textbook from the late 40s, early 50s at Yale. Probes for coupling energy into a waveguide, in this case we're talking about the surface waveguide, are mode sensitive. All right, you got to make a probe. If you're going to excite a mode, your probe has got to match the mode somehow. And that's why we said earlier on today that the Zenek wave is the excitation of the pole in Sommerfeld's solution. If you excite it, if you don't excite the pole, you won't see the Zenek wave. Well, same thing happens for any waveguide mode. The probes are mode sensitive. The probes for coupling energy into a waveguide are mode sensitive, and they must be fed with currents or voltages that have relative phasing of the fields of the mode to be excited. For example, look, this has nothing to do with Tesla. This is ordinary waveguides. This is true for all modes. Here's the TE10 mode and the TE20 mode in a waveguide. In the TE10 mode, notice the structure of the fields, all right? So if you're going to excite that, you need a probe that has currents that are going to be in the direction of the fields here. If you wanted the TE20 mode, you couldn't excite it very efficiently anyway with the TE10 mode. You'd use a different probe structure. What's critical are the positions of the probe elements and the modes. Now notice the phase here, that down on this side, up on this side. Of course, they're oscillating. But the magnitudes and phases of the probe are critical to exciting the waveguide mode that you want to excite. Now, the second thing is this comment from Dr. Gubau. He says, look, it is in general necessary to build up a field. Got that? You're building up a field which matches that of the surface wave. Efficient excitation is a matter of field matching and not, and we understand underscore not, as one can find occasionally in the literature. It's not a matter of impedance matching. And people have tried to build Tesla stuff and gone through moving heaven and earth to try to do impedance matching and gotten a 0 for it. By the way, if you look in the background here on the blackboard, you can see that what Zenek is exciting. He's describing this little horn antenna with a single wire train. So he's got a surface wave on wire here that he's describing in this lecture. This is W.W. Hansen, who's really, he's the father of the cavity resonator. Now, cavity resonators were first described analytically, I believe, by J.J. Thomson back in the early 90s, but not as circuit elements. And Hansen really is the first guy to he wanted to build, tune circuits at microwave frequencies, and that drove him to cavity resonators. And the Qs go from lump circuits with Qs of, 10, 20, 30, 100 to Qs of, 10,000, 20,000, whatever. He was also with the Varian brothers in the invention of the klystron, the microwave landing system at MIT, Doppler radar, linear accelerators at Stanford University. He got his PhD at Stanford, and then he did his postdoc. For those of you that are mathematicians, he got his postdoc with Philip Morris at MIT, and that's the Morse of Morse and Feshbach. Okay, but look, he's been recognized as the father of microwave electronics, microwave engineering. But this is what he said, and he told this in his series of lectures at MIT early on in the MIT Rad Labs here. The first thing to learn about microwaves is impedance can't be used as a substitute for thought. You have to know what you're doing. All right. So this puzzling assertion was a source of embarrassment for many of us for many years. Tesla said, I consider this to be extremely important. All right. If he thought it was extremely important, pay attention. Wireless waves are the same character as light waves, only they're not transversal but longitudinal. And what I think he meant was the polarization is not transversal but is longitudinal. All right, so here's what we're trying to explain. Here's the picture from the Century magazine. This is out there 914 meters away from the transmitter. We've got a 10-watt light bulb down here. It's link coupled by 3 turns to this coil. It's about somewhere between 6 or 7 feet high. And there's a ground stake that it's connected to, probably back into the lake. I don't know. This is from June 1900. And the picture is taken somewhere near sunset. Tesla describes this in the diary. So here's our Zenek wave, his expression for it at the top. And here's our E field propagating to our receiver. We are interested in, this is the light bulb. We are interested in the waveform in the light bulb, which we represent as a resistor, and we want to calculate the power in that coupled load. All right, the first thing we can do is use the previous expression for this. We know how much current, we know the power that Tesla's running. He's got a 200 kilowatt transmitter running at 5%. He explains this to you. So he's running at about 10 kilowatts. Now realize, somebody's going to say, oh, 10 kilowatts, we can light up a light bulb 1,000 meters away with a 10 kilowatt transmitter. And I'd say, wait a minute now, wait. You're thinking of AM broadcasting with 120 radials and a quarter wave tall tower. This is an incremental stub antenna. At best, it's 143 feet high. The frequency is 129.5 kilohertz. H over lambda squared is a tiny number. And he doesn't have 120 ground radials on this thing. He's got this thing somehow or other tied into a ground stake with probably about 6 ohms of ground bed resistance. So this is not your conventional AM broadcast transmitter, and you're measuring the field strength predicted from Zenek's expression. The field strength here at 914 kilometers is a field strength of about 7 volts per meter. Okay. So down at the receiver, we have an effective height for the receiver. It's much, much less than a tenth of a wavelength. And we could make a Thevenin equivalent. So the Thevenin equivalent ought to be the line integral of E dot dl, which is for the incident field, it's approximately the incident E field, 7 volts per meter, times the height of the thing in meters. And we know our ground bed resistance. The Thevenin equivalent, we ought to have the input impedance of this thing. And we can calculate the power now delivered to a load over here. And here it is. Except not quite. There's something else. And that's this. That the Thevenin input impedance into this thing has both a resistance and a reactance. And the reactance is the capacitive reactance of this short structure. Look, the E fields from the background field of the Earth is around 50 volts per foot. 50 volts per foot. It's about 200 volts between your feet and your head. Why don't we use that E field to to light up light bulbs and do things? And the answer is because that's a DC. It's static. And the capacitive reactance to get any current to flow is virtually infinite. It's huge, teraohms, gigaohms at least on a rainy day. And we can't draw much current, even at that voltage, through the series capacitive reactance. But Tesla's not at DC. He's at 129.5 kilohertz. And so the technique is something he did all the time. You could use a matching network. He could have used a transmatch to do it. So we can take the high impedance at the input end and advance essentially through our matching network to get a low impedance at this end. And that's where that's where the current is in the coil that he's going to link couple into the light bulb. This is the waveform of the signal in the light bulb. It's a damped wave train. And we're going to represent that as an RF pulse duration tau with a period of t. And it's a finite power signal. It's not a finite energy signal. It's a finite power. So we can do a Fourier series representation of it, just like you do as an undergraduate. Here's the standard waveform. We'll convert our integration from the period to actually the duration of the pulse. Do the integration and you get a pair of sinc functions, sine x over x, for negative and positive frequencies. So, this is a homework problem that every EE junior does in their linear systems course. You recognize that, of course. Now, I'm going to plot that instead of like we have here with a linear amplitude spectrum. We're going to plot this with a logarithmic spectrum. So you can see the sidebands are way down, 20, 30, 40 dB down. But here's the power. We get about 4.7 watts at the fundamental. Realize we've got a negative half spectrum over here. Well, that only gets us to about 8 or 9 watts. We can add in all the power from all the sidebands. This is Parseval's theorem. Okay, so Parseval's theorem permits us to calculate the actual power in the light bulb here. We want that light bulb to come on. And when we do, it comes on. We've got 10 watts and it'll light up. What am I saying? What I'm saying is this. If you do the wave propagation calculations for the experiment that's there on page 356 or so of the Colorado Springs notes, you will get the numbers that he's measuring. Okay, so I think we have a logical justification for the experiments that he conducted there in 1899. Now, this is Tesla's explanation. The coil shown in the photograph has its lower end or terminal connected to the ground and is exactly attuned to the vibrations of a distant electrical oscillator, 914 meters away. The lamp lighted is in an independent wire loop, so it's inductively coupled. Realize this is a vertical resonator, voltage max at the top, current max at the bottom, and it's resonant. So he can do a link couple down here at the bottom. The lamp lighted is an independent wire loop energized by induction from the coil excited by the electrical vibrations of the vibrations transmitted to it through the ground. And again, what we're saying is by means of the ground from the oscillator, which is worked to only 5% of its full capacity. What was the full capacity? Around 200 kilowatts, he tells us. 5% of that's 10 kilowatts. So he's explaining this in June of 1900. Again, if you do what Tesla said he did, you'll see what Tesla said he saw. Tesla explains to his attorney in 1916, that little lamp's nothing spectacular, but this is a great experiment marking an epoch in the art. This coil I can place at the antipode. Aha, we're doing wireless power at this point. Now we've got to be careful before we start feeling our oats. Irving Langmuir was an engineer. Actually, he was a chemist. I think got a Nobel Prize in chemistry, if I'm not mistaken, at General Electric. And in 1953, he gave a famous lecture on pathological science. And this is what he said: people are tricked into false results by subjective effects, but no dishonesty is involved. Wishful data interpretation. We got to be careful. Are we manipulating stuff and getting wishful results that justify Tesla? We got to be careful. All right. Lev Landau, of course, Nobel Prize in early 60s for his work on superconducting fluids, I think it was, made a comment about cosmologists. His comment was, often an error, never in doubt. The comment, I think, was actually made by John Maynard Keynes talking about economists or maybe even politicians. Often an error, never in doubt. We got to be careful. Have we, when we do a calculation and the calculation comes out and seems to verify the experimentals and the way we're framing our explanations, have we overstretched? Well, let's see. We'll pursue that. When Margaret Cheney wrote her book on Tesla, Man Out of Time, she took this picture to the best experts she knew at, I'm not sure whether she did the ones in Colorado or whether it was at SRI, the Stanford Research Institute, because she talked to people at both places. And she writes in her book, she says, in examining the photographs of the experimental station at Colorado Springs, it is apparent to experts that he did not employ apparatus essential to the launching of such waves. And the comment was, at the frequencies Tesla was using, such launching apparatus would be an enormous structure. We're talking 10 kilohertz to 100 kilohertz. Think of a quarter wave monopole to be able to do if it's a radiation. Well, that's the flaw, I think, that the experts had, and we say not so. If the criterion is Zenith mode longitudinal ellipse matching, not radiation. If we're going to match ellipses the way Gubow said, we don't need a quarter wave monopole with 120 ground radials and what have you to launch the power in that mode. Tesla said this: a great many engineers are in doubt as regard to the possibility of this achievement, and yet it is, as with everything else, very easy once you know how. Well, okay, that's nice with pencil and paper or computer simulations. Let's do the real thing. So the first thing we did was we tried replicating the Prospect Lake demonstration, again at 50 megahertz, because that's where our apparatus worked. And in October of 2014, we did this in Plymouth, New Hampshire. And we were using the same Tesla waveguide probe and lit up a light bulb out at, I think it was several hundred feet. A few years later, in May of 2017, we did the experiment at 6 meters, wavelength of 6 meters again, to realize Tesla's transmitting distance was about 0.4 wavelengths at 129.5 kilohertz. This experiment we're going to see is lighting up a light bulb out at a distance of 15.2 wavelengths at a frequency of 50 megahertz. Here's a transmitter. By the way, this is E-field magnitude versus range. And we're going out, 10 feet, 100 feet, 1,000 feet. Well, we'll make it out to about, here's 100, 200, 300, 400 feet is where our light bulb, you can see the light bulb at the various stages. And when we measure the field strength going out, we'll measure the curve But what we wanted to see is lighting up the light bulb as we went out. Now, we got a little video of that right here. And what we'd like to do is show you the video. Here's our transmitter back here. I think we may have been running a kilowatt. I'm not sure. And here's our little receiver. We've got a half-wave dipole for the receiver to make it resonant. And I think it's a 3-watt light bulb or a 5-watt light bulb. And no, it's 3 watts. And a matching network to get our impedances matched.
All right. Go ahead. Okay, now we're on. How far are you? About 15 feet, 20 feet maybe?
About 20, 25 feet.
Okay, let's go ahead and move back. I think you're on the ground there, down there. I'm going to get over this side to give perspective on how far we are away from the probe at this point. So yeah, it's over there a ways. Keep going.
Yeah, so we're at about 10 wavelengths.
See, this way you can actually talk about how far you are out when you just, you know. At some point it's supposed to die on us, isn't it?
He's out at the knee in the curve.
Yep. Just
Okay. Well, we had to use this quote from Sherlock Holmes. How absurdly simple, I cried. Quite so, said he. Every problem becomes very childish once it's explained to you. It's from The Dancing Man. Tesla said, as to the transmission of power through space, that's a matter which I considered certain, absolutely certain, years ago. Tesla's counselor, the lawyer, said, well, what was the distance from the receiving to the sending station in the 1899 Colorado test? Could you give the number of miles approximately? And Tesla says, 10 miles or so. So he claimed that he was able to transmit over at least 10 miles. And again, if you do what Tesla said he did, you'll see what Tesla said he saw. There's a little aside we'd like to do about surface waves, and this involves Guglielmo Marconi and the Zenek wave. This is called the Marconi bent antenna, and it's the one that precipitated the paper by von Herschelmann in 1911. This is an actual Marconi discovery and invention. So many of Marconi's inventions were, let's be kind and say, copied from other people. This is something Marconi actually discovered himself. The Marconi bent antenna was something that gave something new in RF propagation, that is directivity. And he discovers this in 1905. And he had been looking at quarter wave antennas. This is at Poldau in England, way out on the western tip of England. And he took his quarter wave antenna and he bent it over. Now, the total length of the wire is still 90 degrees, but he only went up about 15 degrees at most, fifth of a wavelength or so. Well, this is still huge, because when he does this down at frequencies like 15 or 20 kilohertz, this was huge. Now, what he discovered was that it was directive, propagated in more or less in one direction. Now, what von Herschelmann did, there was no explanation for this antenna, by the way. And what von Herschelman did was he looked at the Marconi structure and solved for the current, not on the structure, but in the ground. And what he found was this current distribution in the ground. And this was vertical current in the ground. So the idea was then we've got a 3-element array here with positive current, vertical current. This is the center point on this structure, plus the vertical current over here. And the end result was you got a phased array. This curve on the left is probably the first antenna power pattern ever made. And it was published in the Proceedings of the Royal Society in 1906, I guess. Here's von Herschelman's calculation based on what he was able to derive in 1911. So you can see they're pretty close to the same. Now, directivity from an antenna system was a big deal back then. Also in 1905, Ferdinand Braun at Strasbourg was working with phased arrays, and Braun and Marconi share the 1909 Nobel Prize for their contributions to wireless telegraphy. There's more to this result. By the way, what you get from this is not a radiation pattern per se. It was the excitation of a xenic surface wave. Marconi then went, I think, in 1911, and he builds this at Clifton, Ireland. He got as close to North America as he could get. It's on the western coast of Ireland. And he builds the same antenna. It's huge. It's tough to see from this picture. I think this was published in Scientific American back in that period of time. It gave him the strongest signals he could get in North America from Europe at that point in time. He didn't really understand what was going on, though, and the notion of a surface wave, I don't think he ever grasped. He went down to Coltano, Italy. By the way, the one in Ireland, was it the Irish Republican Army? They had a Revolutionary War or something in Ireland, and a bunch of the Irish Republic Army, whatever, went in. This house was filled with just a humongous bank of capacitors, and they shot it all up, and they had a fire and other stuff. And bottom line was Marconi left Ireland. So he builds these, I'm going to say smaller ones. These are still big. These are like the Clifton ones in Coltano in Italy in 1911. And he uses those to transmit down to the Italian colony in Ethiopia, and the other one is set up to talk to England and on to North America. And then in 1922, when that thing happened in Ireland, he builds this humongous one for I think for the Vatican. And the amazing thing about it is it doesn't work. It doesn't work at the VLF stations, and it ends up being just a top-loaded vertical monopole after all is said and done. And I don't believe that Marconi ever pursued the xenic surface wave that would have been available to him if he had pursued that. Now, okay. Couple more mysteries here. The mystery of the O'Neill's anecdote, the 26-mile, 10-kilowatt bank of light bulbs. Those of you that have read O'Neill's biography of Tesla, which I think is probably one of the best ones to read because it has the right flavor. O'Neill knew Tesla personally. John O'Neill had received a Pulitzer Prize for some work he had done about 6 or 8 years earlier. He was the science editor for the New York Herald Tribune, and he wrote this about Tesla in his 1944 biography. Tesla tested his power transmission system at a distance of 26 miles from his laboratory, and he was able to light 200 incandescent lamps. That's impossible. Well, can you do it with this TM surface wave is the question. Can we put some numbers in it? We're beginning to feel our oats now, and we have some confidence in our arithmetic. Hugo Gernsback describes it, and he says it was 15 miles. Slavko Boksin, who wrote a biography of Tesla in 1932, says 30 kilometers. And then his Andre Blondel in 1936, he says, Tesla did it 20 miles, 33 miles. Notice the distances are somewhat different. Now, if you're a defense attorney, this is what you want to hear, because it implies there's no collusion among these people. Whoever they heard it from, however they heard it, the story was from different sources. Again, Tesla's lawyer said to him, what was the distance that you did at Colorado Springs? He said, 10 miles or so. Okay, well, what's 26 miles from Colorado Springs? We want to see this wireless power demonstration, 26 miles, and we want to see 250-watt lights, 10 kilowatts received. Is that possible? Well, if you look at the map, and of course we're talking about railroad trains in 1899, if you're going to do this experiment, look at what you got to lug out to the field here. You're not talking about a field strength meter. You're talking about a big coil, 7 feet high, 6 or 7 feet high, wound with number 6 copper wire. This is going to be heavy. And you got to have ground stakes and sledgehammers, and don't forget your bank of 250-watt light bulbs. So more than likely, you're not going to do this with a horse and buggy and going out 26 miles. So the question is, well, if you're at Colorado Springs, you're probably going to take the train. Where can you find a good site to do this experiment 26 miles away? Well, it turns out, okay, Colorado Springs to Denver, there's a train line that goes between the two. And it turns out that it's 24 and a half miles from downtown Colorado Springs. Tesla's about 1.5 miles to the southeast of Colorado Springs, where his experimental station was set up. And it's 24 and a half miles up to this place called Palmer Lake. Now, Palmer Lake was a lake that was there along the train line, and it was a place where the trains would stop because they could take on more water for the boiler for the trains. And here's a picture taken from sometime around 1900. Notice there's been a fire there, and this is kind of a famous picture from that point in time. Here's the railroad station along the side of the lake. Here's a more recent picture, and of course, all the railroad station stuff is gone. This is the lake. Here's the trail. Colorado Springs is off here, and Denver would be down here. And so the train goes around Palmer Lake. Here's a picture of a site that is on the north side of Palmer Lake that would be, hey, this would be appropriate for Tesla to do this. Well, all right. Let's calculate the field strength. Here's, again, Zenek's expression, and we're going to use 26 miles, which corresponds to 41,834 meters. Okay, so here we go out 26 miles. Here's 10 miles, 110, 100. Okay, so here's 20 miles, 26 miles right here. What's our field strength? Well, how much power are we going to run? I would say it would be reasonable to let Tesla run full power, the 200 kilowatts. And he tells us in many places how much current he had at the base of his antenna at 129.5 kilohertz when he's running that much. And the number he gives, for example, in the day he receives the Edison medal, he gives the number of 1,100 to 1,200 amps. So I'm going to use 1,200 amps RMS and calculate the field strength here. Use the 1,200 and the ABB. Remember, that was minus I naught gamma over 4. And the field strength works out to be about, it would be 10, 20, 30, 30.2 volts per meter. Now, that's a humongous field strength. Yes, if he's using a quarter wave tower with 120 ground radials, here would be the field strength. Here's the Norton radiation field. But it's not radiation, it's a TM guided wave. all right, at 129.5 kilohertz. We used a conductivity of 8.8 millimoles per meter with an epsilon of 15 at this frequency. Okay. All right. Now, if we're going to do the Thevenin equivalent of the receiver, we've got to know how tall his receiving structure is. And here's a couple of pictures from Scientific American. This is February 24, 1900. It's on page 117. And it was also in Tesla's big scrapbooks. This describes the captive balloons that were sold to Tesla. 2 balloons were built for Mr. Tesla to experiment with at Colorado Springs. That's in the Scientific American. Now, we know from the correspondence between George Scherf, who was at Tesla's laboratory in New York, and the Colorado Springs laboratory, we know from there that Tesla actually bought 4 balloons. I think he paid $50 a piece for them, as well as other accoutrements, pipes and things for the balloons. Now, early on, Tesla says the balloons aren't working too well. But if he ever got the balloons to work, let's just assume that's part of this experiment. What was the nature of the balloons? Well, we're told that they flew the balloons at Coney Island in New York to 1,000 feet. They used 1,000 feet of cable. This was apparently a popular ride at Coney Island. And they would put people in the balloon and run them up 900 feet and bring them back down. It took a minute to go up and a minute to go down, and they let them stay up there for 3 minutes and sitting in the basket. And here's a picture taken from this. For those of you that like colorized pictures, Kenny colorized it so that you could see Coney Island in 1900 when this picture is taken. But this is what Tesla had available to him. Okay. So conceivably, he could have used an E.DL that would have been 900 feet if he needed it. Well, when you do the calculation, we're going to use a dummy load. Tesla describes the light bulbs in the diary in many places. The light bulbs have about 300 ohm impedance, 50-watt bulbs. If I take, I'm gonna make a dummy load here that I'm gonna try to match to my ground bed resistance. 300 ohms and 300 ohms is 600 ohms. And if I put 100 of them in parallel, I've just used 250-watt light bulbs, and I've got a load impedance of 6 ohms that I can match to my ground bed resistance of 6 ohms. If I do the same matching technique that we used before, where we actually go in the Smith chart and bring the structure into resonance here, okay, to overcome any capacitive reactance we may have. All right, so the conclusion is I can specify the amount of power in my dummy load and the load resistance and the incident E field for the power that I'm running, and calculate how high, this is how high I have to run my balloon as a function of distance away. What height do I have to have so I can deliver 10,000 ohms or 10,000 watts to a matched load, a 6 ohm matched load? And the answer is you need 50 feet. 50 feet? Well, he's got 1,000 feet available to him. If he wasn't optimized in his tuning, he could have easily gone to 100 feet or 200 feet or whatever, which would have been more than enough to have delivered the 10 kilowatts. Well, do you really believe it? And the answer is, maybe. So again, we're back to Benjamin Franklin. Let the experiment be made. All right. Let's see if we can really do it. So we'll see. We haven't done that experiment yet, but we're back to Dr. Marencic. And in 1986, at a symposium at Zagreb, Dr. Marencic published the following comment. He said, Tesla waves, if we may be allowed to use such a name, are in fact surface waves in modern terminology. Study is needed, and we hope that it will be done in the near future. Well, we're now about 40 years later, and I think we've got our arms around the beast. A couple of other things to notice. First, let's plot the attenuation in dB here versus frequency for a wave to go from wherever our transmitter is to the antipode and back. And we'll assume the whole Earth is made out of dirt. Okay, so we can do a little bit better than this. But in Tesla's in his 1905 patent, he says, stay below 20 kilohertz. I would say that the frequency should be smaller than 20,000 per second, though shorter waves might be practical. In another place, in an article, and I've got it referenced here, it says, look, with waves of 1 megahertz, okay, let's see, this is frequency here, 10 kilohertz, 100 kilohertz, 1 megahertz. Notice the attenuation. This is minus 100 dB of attenuation. With waves at 1 megahertz, economic transmission of energy is out of the question, the loss being too great. When using frequencies of 50 kilohertz, it's still noticeable. 50 kilohertz, let's see, 50 kilohertz is in here. Yeah, it's still noticeable. It is, though, not a serious drawback. With frequencies of 25 kilohertz, it becomes quite insignificant. All right, look at 20 kilohertz. Here's 20 right here. We're down 3 dB. Okay. It becomes quite insignificant. And on this fortunate fact rests the future of wireless transmission of energy. The bottom line is if you can stay below 20 kilohertz, maybe below 10 kilohertz, the attenuation from here to the antipode and back is essentially fractions of a dB. All right. Ferdinand and Barlow wrote this in 1956, published in, I think, the IEE in England. A surface wave is characterized by its ability to propagate along an interface between two different media without radiation, so that the only flow of energy normal to the interface is that required to supply the losses in the media concerned. Tesla stated this in 1905 a little bit differently. He said, a popular error is that the energy of my wireless power plant would dissipate itself in all directions. That'd be radiation. This is not so. My experiments have shown that the entire electrical movement which keeps the whole globe a-tremble can be maintained with but a few horsepower. You got to pay your dues to the transmission system. We do that already with the North American power grid. In 1917, he said the efficiency of transmission can be as high as 96 or 97%, and there are practically no losses except such as are inevitable in the running of the machinery. In my system, no power is lost. When there are no receivers, the plant consumes only a few horsepower necessary to maintain the electric vibration. He's describing a transmission line mode. All right. What about global resonances? We're on our way here. We're almost done. This is Tesla's scribbled notes on the Waldorf Astoria stationary. Dr. Morenchich made that famous back in the 80s. But if I have a transmitted pulse, it will propagate peripherally and reflect off the antipode and come back and set up a standing wave here. We had a patent examiner say, what's it reflecting off of? What's it reflecting off of? Well, think of this as a big marble, and we've got a microwave beam that's illuminating it, and the open circuit at the other end of the transmission line will reflect off of that. If you don't want to believe that, you can think of the peripheral waves as going around and coming back, okay? Like creeping waves of in microwave optics. This picture of the Sherman-Williams paint gives you an idea of a peripherally dripping wave around the planet. But that's a standing wave approach. And Tesla set up here's the memo. It's the Tesla Flowers memo from July 16, 1925. Flowers was working at the Philadelphia, was it Navy Yard, or maybe it was the airport or whatever, but he was trying to get some money to set this up as an experiment, and I guess it got turned down. But the idea was I'll have this concentric path, and I'll set up a standing wave here and show that I can pick up the power anywhere around this closed transmission line. Well, what about the pathological science stuff? I think, again, people are tricked into false results by subjective effects and no dishonesty involved. They just, it's pathological. It's a disease. Wishful data interpretation. I think at this point we're feeling our oats good enough to be able to say, wait a minute now. Let's turn this around onto the great sign error myth of Norton and Burroughs and Vanderpoel and the folks in the 20th century. What if they were the ones? They committed pathological science. They were tricked into false results. That's what happened with Charles Burroughs at Seneca Lake. Here's the letter from Norton to Nature in 1935. He says, this letter is to point out an error in sign in Professor Sommerfeld's 1909 paper. And this marked the beginning of that sign error myth that is propagated through 20th century electromagnetics. And here in 2004, Dr. Collin said, there is no sign error. The famous sign error is a myth. Hey, those were the guys. They committed pathological science. They fooled themselves. And as a grad student, kind of learning that stuff, I'd say we were all tricked by the crucial experiment. Crucial experiment. That's the phrase that Burroughs used and Jim Waite used and many other people used to describe the Seneca Lake experiment. It was one of the most important experiments conducted during the 20th century. It just framed the whole way electromagnetics and communications would be taught for the next 70 years. They were tricked into a false conclusion, and their results were in error. And it looks to us like, hey, wait a minute, Zenek, Tesla, they were right. Now, we need to say what wireless power is not, okay? Wireless power is not magnetic induction or mutually coupled flux like MIT, the Whitetricity. It's not a radiation field like the microwave beam used by Raytheon when they powered a helicopter, or what the Australians are now trying to transmit power. It's not a laser beam. It's not RF energy harvesting like the PowerCast people at Pittsburgh are doing. Wireless power is not antenna near-field coupling like folks in China and Japan have reported. It's not earth resistance conduction like James Bowman Lindsay tried in the 1840s. It's not Sipes experiment, that is a single wire transmission like the folks in Korea are doing today. It's not a Gubow line like Zenek student Gubow did in the 30s and 40s. It's not Schumann cavity resonance like Thomson and Schumann and Val Fitch, who mentions in Jackson's electromagnetics. It's not charged diffusion from the Earth. The issue in all of these is transmission loss. None of the above have wireless system efficiency over long transmission distances. In 1927, Tesla said, so unsound are these schemes that I'm at a loss as to how they could pass the scrutiny of competent experts. 18 years to the day after Tesla discovered the standing waves, he saw standing waves, terrestrial standing waves excited by lightning on July 4th, 1899. On July 4th in 1917 is when this tragedy occurred, and Tesla's Wardenclyffe facility is blown up. This was the ignorant destruction of the 20th century. Can you imagine how the world would have been different over the 20th century if we had wireless power would have occurred 100 years ago? Instead, here it is. Some people, what did they recover? They recovered about $2,000 for the lumber and junk that they were able to get out of blowing up Tesla's facility. Look at the people that are present here. Look at these boys up on the top of the railroad depot, and there's some people down there on the fence. And Look at these two guys here. Look at the body language of this guy. I swear he's a salesman or something, maybe a politician, standing there in his Panama straw hat on the 4th of July, watching Tesla's tower being blown up. Look at the giddy grin on this fellow over here on the right that's turned around. They didn't have a clue of what they were looking at. Here it is, 1917. This is World War I. They are witnessing the destruction of 20th century civilization. And the last 100 years, we got what we got, not what we could have had. All right, here's Tesla. We have this in a piece of communication going back and forth between George Cerf in New York City and Tesla at Colorado Springs. And Cerf is expressing his concern. And Tesla writes back, "Don't worry about me. I'm about a century ahead of the other fellows." Well, that was in 1899. That was 126 years ago, 125 years ago. He was right. He is a century ahead of the other fellows. What's engineering? Tesla was an engineer and a scientist. Engineering has been defined as that profession which utilizes the resources of the earth for the benefit of mankind. This picture was taken from the western side of the Hudson River, looking back at New York City. I think I have the date written down somewhere, but it's about 10 years or so ago when they had a blackout. It was probably the first time that a lot of people in New York ever saw the moon or the stars. But that's what we would have for civilization without Tesla. Okay, what drove him? The president, I have a couple of comments here from presidents of in this case, the American Institute of Electrical Engineers. This guy was also president of Cooper Union College. He said, look, Tesla solved the greatest problem in electrical science of his time. The president of the AIEE in 1917 said this: Tesla's great conception of the rotary field, and isn't it interesting he said rotary field, because now we know Tesla invented both a rotary magnetic field that gave us motors and the rotary electric field, which made the Zenek wave possible. Tesla's great conception of the rotary field was one of the greatest feats of imagination which has ever been attained by the human mind. Where was he going with all of this? Well, 3 years ago, there was a proposal in the IEEE. They proposed a hardwired global DC supergrid to be able to get the energy from wherever it could be generated to wherever the population centers are. And it reminds you for all the world of Buckminster Fuller's comment that we need to make the world work for 100% of humanity in the shortest time possible. But the thing is, you don't need wires to make this supergrid happen. What was beyond Wardenclyffe? Look at every point of light here on the planet. Imagine if we could take the energy sources in Indonesia or wherever the oil wells and gas wells and wind power happens to be on the planet and distribute it to all of humanity everywhere. Tesla said it would seem as though the Creator himself had electrically designed the planet just for this purpose. See the excitement coming. He also said the experts must in time, and I think the time has come. The experts must in time come to the same conclusions. Sooner or later, my power system will have to be adopted in its entirety. And our experience has been, and people said ball lightning doesn't exist. Well, here you're looking at it. We found like bubbles off of Lawrence Welk's bubble machine. You can make fireballs. If you do what Tesla said he did, you will see what Tesla said he saw. Tesla wrote in 1919, "Those who are well informed know that my ideas have revolutionized the industries of the United States." Yeah. What drove Tesla? In his second lecture at Columbia University, Tesla said, this is in May 20th, 1891, There is no subject more captivating, more worthy of study than nature. To understand this great mechanism, to discover the forces which are active and the laws which govern them, is the highest aim of the intellect of man. Thank you for your patience. We hope this helps understand Nikola Tesla.